Hi, I'm Julian Kelly, and today, on behalf of our amazing team, I'm proud to announce Willow.
Alphabet shares are higher after announcing a quantum computing breakthrough, unveiling its new chip, Willow.
Google just achieved something that's been impossible for almost 30 years in quantum computing, and almost nobody's talking about what it really means. While everyone's focused on AI and ChatGPT, Google's team quietly launched a quantum chip called Willow that's completely changing our understanding of what's possible with computers. Here's what makes this so fascinating. Every computer you've ever used, your phone, your laptop, even the most powerful supercomputers, they all work like incredibly fast calculators, processing information as ones and zeros. But Willow, it operates on an entirely different level, using the strange and counterintuitive rules of quantum physics, the same rules that govern how atoms behave at their most fundamental level. And when I say strange, I mean it. These are rules where particles can exist in multiple states at once, where information can teleport instantly across space, and where the very act of observing something changes its behavior. The real breakthrough isn't just that Google built another quantum computer, it's what happens when they make it bigger. See, normally when you scale up any kind of technology, it becomes more prone to errors. Think about it like this: the more moving parts you add to a machine, the more likely something is to break down. That's been one of the biggest challenges in quantum computing for decades. These systems are incredibly fragile, and the bigger you make them, the more unstable they become. It's like trying to balance a house of cards in a windstorm. Add one more card and the whole thing becomes more likely to collapse. But Willow, it completely flips this rule on its head. Instead of becoming more unstable as it grows, it actually gets better at fixing its own mistakes. Google demonstrated this with a series of increasingly larger grids of quantum bits, or qubits. Let's break down exactly what they did, because this is where it gets really interesting. They started with a small 3x3 grid. Think of it like a tiny team of workers. This team could catch and fix one mistake at a time. Pretty basic stuff, but it proved their concept worked. Then they scaled up to a 5x5 grid. Now we're talking about 49 quantum workers all coordinating together. This larger team could handle 2 mistakes simultaneously. But here's the crazy part. They weren't just handling more errors because there were more workers. The system was actually getting better at error correction, becoming more stable and reliable as it grew. It's completely counterintuitive, like having a car that gets better gas mileage the bigger you make it. But they didn't stop there. The team pushed to a 7x7 grid with 97 qubits, and something remarkable happened. This larger system could handle 3 simultaneous errors, and it did it with even greater efficiency than the smaller versions. The connections between these qubits, visualized as yellow lines connecting colored squares, showed how they were working together like a quantum safety net, catching and correcting errors in real time. To really understand how revolutionary this is, we need to talk about scale. When Google tested Willow against traditional supercomputers, the results were mind-bending. Problems that Willow solved in under 5 minutes would take our fastest supercomputers longer than the age of the universe to figure out. We're not talking about being twice as fast, or even 1,000 times faster. We're talking about calculations that would take 10 followed by 25 zeros years on traditional hardware. That's not just an improvement, it's like comparing the speed of light to a snail's pace. Now, whenever there's a breakthrough like this, people immediately jump to worst-case scenarios. There's been a lot of panic about what this means for things like Bitcoin security, with headlines screaming about how quantum computers will break all encryption. But that's missing some crucial context. Willow is incredibly powerful, but in a very specific way. It's like having the world's fastest race car, impressive, but not very helpful if you need to move furniture. Breaking Bitcoin's encryption would require a quantum computer with thousands more qubits and capabilities that Willow simply doesn't have. Think about it like this. Bitcoin's security is like a massive bank vault with millions of possible combinations. Current computers would need centuries to try all these combinations. While Willow is incredibly powerful, it's specialized for very different types of calculations. It's like trying to use a Formula 1 car to crack a safe. No matter how fast that car is, it's just not the right tool for the job. To actually break Bitcoin's encryption, you'd need a quantum computer with way more qubits than Willow's 105, much better precision. Willow still makes too many mistakes for this kind of work, and specific capabilities that Willow doesn't have. But here's where it gets really interesting. And I mean really interesting. When you look at how Willow achieves these impossible calculations, you start running into some mind-bending questions that challenge our understanding of reality itself. How can a computer solve problems that should take longer than the universe has existed? Where is all that computation actually happening? One fascinating theory, proposed by physicist David Deutsch, suggests that quantum computers might actually be tapping into parallel universes to perform their calculations. I know this sounds like science fiction, but stay with me here. Think about solving a maze. A regular computer would try one path at a time, like you or I would. But a quantum computer? It's as if it's trying every possible path simultaneously, pulling the correct answer from countless parallel realities. This isn't just theoretical hand-waving. It might actually explain how these machines can perform calculations that should be theoretically impossible in our universe alone. It's like having infinite versions of yourself, solving the same problem in slightly different ways, and then somehow getting all the answers at once. The fact that Willow can do calculations that would take longer than the universe has existed suggests something rather strange and fascinating is happening behind the scenes. Looking at Google's quantum roadmap, we're witnessing something like the early days of flight. Willow has already achieved what we call quantum supremacy, proving it can do things classical computers simply can't. It's like that first Wright brothers flight at Kitty Hawk. Brief and limited, but proving that powered flight was possible. That's milestone 1, proving quantum computers can actually outperform classical ones in specific tasks. But the real challenges and the really exciting developments lie ahead. Right now, we're deep into milestone 2, quantum error correction. Current quantum computers are incredibly error-prone. Imagine trying to build a computer where the slightest vibration, temperature change, or electromagnetic interference could corrupt your calculations. It's like trying to perform brain surgery while riding a mechanical bull. What makes Willow so revolutionary is that it's showing us a path forward, proving that we can actually make these systems more stable as they grow larger, not less. The next big challenge is what scientists call a long-lived logical qubit. Milestone 3. Think about your phone's battery. It stays stable and reliable for hours or days at a time. But current qubits? They're more like trying to keep a soap bubble intact in a windstorm. They lose their quantum properties incredibly quickly. We're talking microseconds here. Building qubits that can maintain their quantum state for longer periods is crucial for any practical quantum computer. Then there's milestone 4, logical gates. These are like the basic operations in a classical computer, addition, subtraction, that sort of thing. But in the quantum world, every operation has to maintain the delicate quantum properties while still being precise enough to be useful. It's like trying to perform microsurgery while dancing. You need both precision and flexibility. The engineering scale-up, milestone 5, is where things get really ambitious. It's not enough to have 1 or 2 stable qubits. We need thousands or even millions working together reliably. This is like going from building one perfect engine to mass producing them while maintaining the same level of quality and reliability. And finally, there's milestone 6, a fully functional quantum computer that can solve real-world problems. This isn't just about raw computing power, it's about creating a system that's reliable enough, stable enough, and practical enough to tackle problems that matter. We're talking about simulating complex molecular interactions for drug development, optimizing financial models in ways that could revolutionize the economy, or solving climate modeling problems that are simply too complex for classical computers. But here's what makes this all so exciting. Willow isn't just another step along this path, it's potentially a leap forward in how we think about quantum computing itself. The fact that it gets more stable as it grows larger challenges our fundamental assumptions about how these systems work. It's like discovering that airplanes actually become more fuel efficient the bigger you make them. It completely changes the rules of the game. The implications of what Google's achieved here go way beyond just building a better computer. Willow is showing us that the impossible problems we've been stuck on for decades, from discovering new medicines to predicting climate patterns, might actually be solvable. We're not just watching some incremental tech upgrade, we're seeing the first glimpses of what could be the biggest shift in computing since the invention of the microchip. And while there's still plenty of work ahead, one thing's clear: quantum computing isn't some far-off dream anymore. It's here, it's working, and it's just getting started.